You're late for a meeting, the Wi-Fi is down, and the only copy of the presentation is on a little stick that fits in your pocket. You plug it in, and whoosh, the file appears. It's like magic, but it's not magic. It's a flash drive. And today we're going to answer the question that's been bugging anyone who's ever stared at a tiny plastic rectangle and thought, what on earth is that thing? What is a flash drive and how does it work? A quick fire guide for the curious, the skeptical, and anyone who's ever tried to plug a USB-A connector into a USB-C port. We've all been there. We'll start by defining what a flash drive actually is, then crack open its tiny brain to see how it stores your data. After that, we'll zip through the different flavors: USB 2.0, 3.0, 3.1, USB-C, and talk speed, capacity, and the quirky little controller that keeps everything running smoothly. By the end, you'll know how to pick the right drive, how to keep it alive, and why you shouldn't use it as a keychain. Trust me, we'll get to that. What is a flash drive? In the most boring of terms, a flash drive is a small portable storage device that uses solid-state memory, specifically NAND flash memory, to hold data. But that's like saying a pizza is a circle of dough with cheese. Let's unpack it. Flash memory is non-volatile, meaning it remembers your cat photos even when you unplug it. It's the same tech inside your smartphone, your SSD, and that one game cartridge you still pretend you'll replay someday. The thing that makes a flash drive flashy is its form factor: a USB connector, Type A, Type C, or Micro B, attached to a tiny circuit board, wrapped in a plastic or metal case. It's designed to be rugged, cheap, and small enough to lose in your couch cushions. Something we've all done, probably more than once. Now, why is it called a flash drive? Because the memory inside is called flash memory, named after the process that programs the cells. It's not because it makes your files go whoosh, though that would be cool. And the term thumb drive, it's just a nickname that stuck because the early models looked a bit like a thumb. So the next time someone calls it a thumb drive, you can nod knowingly and pretend you're an insider. Fun fact, the first commercial USB flash drive hit the market in 2000, created by a company called Trek 2000. Before that, we were lugging around floppy disks, like carrying a stack of pancakes everywhere. The flash drive changed the game, and now we have tiny vaults in our pockets. If you're digging this quick fire dive into the world of flash drives, hit that like button. Your thumbs will thank you. And if you haven't already, subscribe to What Is, so you never miss a tech snack. Ring the bell, and we'll send you more answers to questions you didn't know you had. How does it work? Let's peel back the cover and see the brain. Inside every flash drive are three main parts: the NAND flash memory, a tiny controller chip, and the USB connector. Think of the NAND memory as a city of microscopic doors. Each door can be open, 0, or closed, 1, to store a bit. The doors are organized into blocks, and each block can be erased and rewritten thousands of times, well, until the magic wears off. More on that later. The controller is like the mayor. It decides where to store new files, which doors to open, and it makes sure the city doesn't get too cluttered. When you plug the drive into a USB port, your computer sees it as a removable disk. The USB interface talks to the controller, which then translates those USB signals into commands for the NAND memory. It's a bit like a translator at a United Nations summit, except the translator is about the size of a grain of rice. Now here's where the magic happens. We're leveling. The controller spreads writes across all the memory cells so that no single cell gets worn out too fast. Imagine you have a group of friends and you rotate who brings the snacks. Everyone shares the load and nobody gets stuck with the same duty every time. That's wear leveling. There's also error correction code, ECC, that catches tiny mistakes, kind of like a proofreader for your data. If a stray electron sneaks in and flips a bit, the ECC fixes it on the fly. So even though the memory is cheap, the drive is surprisingly reliable. One more thing. Trim. When you delete a file on a regular hard drive, the space is marked as free. On a flash drive, the controller can actually erase the old data blocks ahead of time, so new data can be written faster. It's like having a janitor who cleans the office before you even finish your coffee. Types, speeds, and capacities. Now that we know the inside, let's talk about the outside. Flash drives come in several flavors, each defined by the USB standard they support. USB 2.0 is the old school classic. It tops out at about 480 megabits per second in theory. Real world, you'll see around 30-40 megabytes per second. It's fine for a few text documents, but if you try to move a 4K movie, you'll have time to make a sandwich. USB 3.0, also called USB 3.1 Gen 1, is the upgrade. It can hit 5 gigabits per second, roughly 500 megabytes per second, so you can blaze through a full album of high-resolution photos in seconds. Look for the blue tongue inside the port. That's the visual cue. USB 3.1 Gen 2, or USB 3.2, pushes it to 10 gigabits per second, and the newest USB 3.2 x 2 can hit 20 gigabits per second. At those speeds, you can copy a whole season of a TV show in the time it takes to microwave popcorn. And then there's USB-C. The reversible wonder. It's not a speed increase by itself, but it can support the fastest standards and also works with smartphones, tablets, and the newest laptops. No more fiddling, plug it in either way, and you're good to go. Capacities range from a meager 1 gigabyte, enough for a single MP3 album, to a massive 2 terabytes. Yes, that's 2 terabytes, enough to hold about 500,000 songs or a small library of video. As of 2026, 1 terabyte drives are becoming the sweet spot for most folks, while 2 terabyte models are for the data hoarders among us. One thing to keep in mind, the advertised capacity isn't exactly what you get. A tiny portion is reserved for the controller's firmware and wear leveling tables. So a 128 gigabytes drive might show up as 119 gigabytes on your computer. That's normal. Don't panic. Usage scenarios. Why would you need a flash drive in 2026? Let's list a few real-world scenarios. 1. Portable workspace. Run a full suite of apps. Think office tools, code editors, even a portable Linux distro, right from the drive. No need to install anything on the host machine. It's like carrying your own computer in your pocket. 2. Bootable rescue media. When Windows refuses to start, a bootable flash drive can be a lifesaver. You can load a recovery environment, run diagnostics, or even reinstall the OS 3. Media library. For those who still love physical media, a flash drive can hold a massive collection of movies, music, and photos to plug into a TV or car stereo. 4. Secure storage. Many drives include hardware encryption or a built-in keypad. Perfect for sensitive documents you don't want floating around in the cloud. 5. Gaming. Some consoles and handhelds support running games directly from a flash drive, freeing up internal storage. And let's be honest, how many of us have used a flash drive as a makeshift keychain? It's tempting, but those little connectors are delicate. If you want your data to survive, treat it like a tiny fragile creature. Don't toss it in a bag with a bunch of heavy keys. Maintenance and tips. Now that you've got the perfect flash drive, how do you keep it happy? Here are a few easy tips. 1. Eject properly. Always use the safely remove hardware option on your computer. Yanking it out while data is still writing is like ripping a book out of someone's hands mid-sentence. Bad news. 2. Avoid extreme temperatures. Flash memory hates heat and cold alike. Leaving your drive in a hot car or freezer can shorten its life. Treat it like a cat. Keep it comfortable. 3. Keep it dry. Moisture and electronics don't mix. If you drop it in a puddle, dry it off thoroughly before plugging it in again. Some people even recommend a quick rice bath. Just don't cook the drive. 4. Backup. Flash drives can fail, just like any storage. Keep at least one backup of any critical data. A good rule: if it's important, it lives in at least 2 places. 5. Format wisely. If you need to reformat, choose a file system that matches your devices. FAT32 for broad compatibility, XFAT for larger files, NTFS for Windows-only use. And always run a quick format for day-to-day use. Full format is only needed when you suspect hardware issues. One more thing: write cycles. Each memory cell can be written and erased a limited number of times, usually between 3,000 and 5,000 cycles. With modern wear leveling, you'll likely never hit that limit in normal use. But if you're constantly filling and erasing a drive every day for years, you might eventually wear it out. When that happens, the drive turns into a pricey paperweight. Let's wrap it up. A flash drive is a portable, solid-state storage device that uses NAND flash memory and a tiny controller to read and write data via a USB interface. It's non-volatile, rugged, and comes in many shapes and speeds. The key components are the memory, the controller, and the USB connector. The controller handles wear leveling, error correction, and data translation, making your little stick reliable. Different USB standards give you different speeds, and capacities range from a few gigabytes to a couple of terabytes. Use it for portable apps, bootable media, extra storage, or even secure encrypted files. Just treat it with care, eject properly, keep it dry, and back up your data. If this deep dive helped you understand the tiny tech in your pocket, give it a thumbs up. Your support keeps us making more videos like this. Subscribe to What Is if you haven't already, and hit the notification bell so you never miss a new episode. Got a question about flash drives or any other gadget? Drop it in the comments below. We love answering the curious stuff. Thanks for hanging out with me. Now go ahead, pick the right flash drive, back up your files, and maybe, just maybe, treat that little stick like the tiny powerful computer it is. See you next time. Imagine you're sitting on a couch. You've got a device in your hands. It's touch sensitive, it fits in a jacket pocket, and you can watch Netflix on it. Now imagine you're trying to write a dissertation, edit a 4K video, or run a complex data analysis. Completely different device, right? Maybe not. Welcome to What Is. Today we're answering one of those questions that sounds simple, but somehow isn't. What exactly is a tablet? And how, actually, is it different from a computer? Sounds easy. But stick around, because by the end of this video, you might realize you've been using the word computer wrong your whole life. What it is. Let's start with the obvious. A tablet is that flat touchscreen device you probably use to scroll through social media, read ebooks, or video call your grandma. Popular examples include the iPad, Samsung Galaxy Tab, Amazon Fire, and dozens of others. They're sleek, they're portable, and they run operating systems like iPad OS or Android. But here's where it gets interesting. When you strip away the marketing fluff and the form factor, a tablet is essentially a computer. And I don't mean that in some philosophical, everything is a computer now way. I mean it literally. The processor inside your iPad, its architecture is remarkably similar to what's in many laptops. The operating system, it's descended from the same roots as desktop operating systems. The apps you run, they're built using many of the same programming principles. So why do we treat them as different categories? That's the question we're unpacking today. Before we get into the differences, let's do a quick history lesson, because understanding where tablets came from helps explain why the distinction exists at all. History. The concept of a tablet computer isn't new. Actually, it's older than most people realize. Back in the 1960s and 70s, researchers were already envisioning portable, touch-sensitive computing devices. Star Trek fans might remember the fictional pads, personal access display devices, that the crew used. That was the 1960s vision. Forward thinking, right? But the first real attempts at tablet computing came in the 1990s. Apple attempted the Apple Newton in 1993. It was a personal digital assistant with handwriting recognition. It was bulky, expensive, and the handwriting technology was generously described as imperfect. Then came the Microsoft Tablet PC initiative in the early 2000s. These were essentially laptops with touchscreen displays that you could fold flat. They ran full Windows, but they were heavy, expensive, and frankly, most people didn't bother. The revolution came in 2010. Apple released the first iPad, and suddenly, whoosh, everything changed. Apple didn't invent the tablet, but they perfected the formula. Intuitive touchscreen interface, long battery life, lightweight design, and an app ecosystem that made the device actually useful for everyday tasks. Within a few years, tablets went from novelty to necessity for millions of people. And here's the key moment. Apple deliberately marketed the iPad as not a computer. Remember the famous ad campaign? It's not a computer, it's an iPad. They wanted to separate the product in people's minds, make it feel simpler, more accessible, less intimidating than a traditional PC. That marketing decision, it shaped how we think about tablets to this day. But is that distinction actually valid? Let's find out. Alright, before we go further, quick break to say if you're new here, welcome. We're building something special at What Is, a channel dedicated to answering life's curious questions in the most engaging way possible. If you want to see more videos like this one, hit that subscribe button and join the community. Now let's get back to it. So what is a tablet really? At its core, a tablet is a portable computing device that uses a touchscreen as its primary input method, instead of a keyboard and mouse. It typically has a flat, slate-like design with a display covering most of the front surface. It connects to the internet via Wi-Fi and sometimes cellular data. It runs a mobile-derived operating system, though that's been evolving. Now, what is a computer? This is where it gets fun. A computer, in the technical sense, is any device that takes in information, processes it according to instructions, and outputs the result. By that definition, your smartphone is a computer. Your smart fridge is a computer. That old calculator you used in high school? Also a computer. But in common usage, when people say computer, they usually mean one of two things: a desktop tower with a monitor, or a laptop. Something with a keyboard, a mouse, perhaps some ports for connecting other devices. So already we see the issue. We're comparing categories based on form factor and usage patterns, not underlying technology. Let's break down the actual differences, real practical differences, between a tablet and what we typically call a computer. Differences. Number 1. Input method. This is the most obvious distinction. Tablets are primarily touch-driven. You tap, swipe, pinch, and drag. Computers, traditional ones at least, rely on keyboard and mouse input. Now here's where it gets complicated. Many tablets now support keyboard accessories. The iPad has the Magic Keyboard. Samsung's Galaxy Tab has keyboard folios. Some people use their tablet exactly like a laptop, but the default experience is different. Tablets feel natural for consuming content, watching videos, browsing the web, reading. Computers feel natural for creating content, writing documents, coding, editing photos and videos. Number 2. Operating system architecture. Tablets run mobile operating systems, whether that's iPad OS, Android, or Amazon's Fire OS. These are designed around touch interfaces and limited multitasking. Traditional computers run desktop operating systems, Windows, Mac OS, Linux, designed around mouse and keyboard interfaces with robust multitasking capabilities. But again, the lines are blurring. iPad OS now supports split-screen multitasking. Windows has touchscreen modes. You can connect a mouse to an iPad. You can use a tablet as a drawing input for a desktop computer. Number 3. Software ecosystem. This is huge. Computers can run full desktop software. Professional-grade applications for video editing, like Adobe Premiere, audio production like Pro Tools, scientific computing, complex databases, full programming environments. Tablets, even powerful ones like the iPad Pro, have limitations. The software is more constrained, not necessarily worse, just different. Touch-optimized apps tend to be simpler and more intuitive, but they don't have the feature depth of professional desktop software. Except, wait, Adobe now makes full Photoshop for iPad. Apple's iPad Pro with the M2 chip can literally run the same architecture of software as a laptop. So we're in this weird transitional period where the gap is closing fast. Number 4, ports and connectivity. Traditional computers have USB ports, HDMI outputs, SD card readers, Ethernet jacks, all sorts of ways to connect to other devices and accessories. Tablets, you've got maybe a USB-C port or a lightning connector. That's it. Want to connect a professional camera? You might need adapters. Want to plug into a projector? Hope you've got the right dongle. But wireless connectivity has improved massively. AirDrop, Bluetooth, Wi-Fi casting, all that works well now. Number 5, upgradability. With a traditional computer, desktop or laptop, you can usually upgrade components. More RAM, bigger hard drive, better graphics card. With a tablet, it's essentially sealed. You can't open it up and swap out parts. What you buy is what you're stuck with, hardware-wise, unless you count the keyboard accessory ecosystem. But those are add-ons, not upgrades to the core device. Number 6, multitasking and workflow. On a computer, you can have multiple windows open simultaneously, easily drag content between applications, use keyboard shortcuts to speed up your workflow. Tablets traditionally made you work in one app at a time, though that's changing. You can run 2 apps side by side on modern iPads, but it's not the same as the fluid window-based experience of a desktop. Number 7, price and accessibility. Here's a practical one. Tablets, especially budget models, can be cheaper than entry-level laptops. You can get a solid Amazon Fire tablet for under $100. An iPad for everyday use is competitive with mid-range laptops, but at the high end, iPad Pro with keyboard and Apple Pencil, you're spending laptop money. Often more. Now let's look at the similarities, because they're actually more significant than the differences. Similarities. Both tablets and computers run on similar underlying technologies. Processors, memory, storage, wireless radios. The fundamental computing architecture is the same. Both can run productivity software. Word processing, spreadsheets, email, video calls. The difference is in degree and ease of use, not capability. Both connect to the internet and can run web-based applications. Both have app ecosystems, though computers also support traditional software installation. You could argue that the category distinction is becoming more about intention and use case than about the technology itself. Here's where I want to make you think differently about this. Remember earlier, I said people use computer to mean desktop or laptop. That's a cultural definition, not a technical one. The tablet is a computer. It's a category of computer. It's a bit like the difference between sedan and sports car. They're both cars. They have engines, wheels, steering wheels. But we categorize them differently because of how they're designed to be used. Tablets are computers optimized for consumption, portability, and touch-first interaction. Traditional computers are optimized for creation, expandability, and productivity. But here's the thing. As technology advances, these categories are merging. The iPad Pro is essentially a touchscreen laptop without the keyboard. Microsoft's Surface devices literally flip between tablet and laptop modes. Chromebooks now have tablet modes. We're watching the categories dissolve in real time. Is that confusing? Maybe a little. But it's also exciting. It means we're getting the best of both worlds, devices that are versatile and adaptable. When to use each. So when should you actually choose one over the other? Choose a tablet when you want something ultra-portable for casual use. Browsing, social media, video, reading. You're a student or casual user who mainly needs email, web browsing, and basic document work. You want a device that's easy for kids or less tech-savvy family members to use. You're an artist or designer who wants to draw directly on the screen with a stylus. You want a secondary device for consumption. Keep it on the coffee table for browsing, or take it to bed for reading. Choose a computer when you need to do professional creative work, video editing, music production, 3D modeling, software development. You need to run specialized software that only works on desktop operating systems. You want to do serious multitasking, multiple windows, complex workflows. You need expandability, more storage, more memory, multiple monitors. You're building a workstation that stays in one place. You need more ports and connectivity options for professional equipment. But honestly, many people benefit from having both. A tablet for casual use and a computer for heavy lifting. That's become the standard setup for many professionals. The future. Where is all this heading? Here's my prediction. The distinction between tablet and computer will continue to blur until it essentially disappears. We're already seeing it. Devices like the iPad Pro and Microsoft Surface are doing things that were exclusive to computers just a few years ago. Operating systems are converging. iPad OS keeps getting more computery features. Windows works better with touch. Chrome OS runs Android apps. The future might be less about choosing between categories and more about choosing the right configuration of a universal device. Keyboard attached or detached, touch mode or mouse mode, mobile app or desktop software. We're already living in that future to some degree. So, what is a tablet, and how is it different from a computer? Here's the simple answer. A tablet is a computer, a portable, touch-first computer. The real differences are in form factor, input methods, software capabilities, and intended use cases. But those differences are shrinking fast. The more interesting question might be, does the distinction even matter anymore? Maybe what we should really be asking is not tablet versus computer, but what kind of computing experience do I need? That's a question only you can answer. Thanks for watching What Is. If you learned something today, share this video with a friend who's still confused about the difference. Leave a comment below with your thoughts. Do you own a tablet, a computer, or both? What do you think about the future of these devices? And if you want more answers to life's curious questions, subscribe to What Is. Until next time, stay curious. Imagine for a moment that you've decided to build the most powerful telescope ever created. You've got an unlimited budget, cutting-edge technology, and the brightest minds on the planet working for you. Where do you put it? Do you put it on a mountain, high above the clouds, away from the city lights? Or maybe put it on a plane, a flying observatory that can chase totality across the sky? Or, and hear me out here, what if you just launched it into space? Strapped a massive mirror onto a rocket and blasted it through the atmosphere, and parked it in orbit around the sun, millions of miles from Earth, where nothing interferes with your view of the cosmos. That's not a hypothetical. That's the James Webb Space Telescope. And it's not alone out there. Welcome to What Is, your guide through the strangest corners of human curiosity. And today, we're answering a question that sounds simple, but will take us from the mountains of California to the edge of the observable universe. What is a space observatory, and how does it study the universe? Origins. To understand space observatories, we need to go back to a time when looking up meant looking through something very, very dirty. For most of human history, astronomers did their work from the ground. They'd build towers, domes, elaborate cathedrals of science housing telescopes that could see, well, quite a lot actually, given the circumstances. But they were fighting a losing battle against Earth's atmosphere, that protective blanket of gas that keeps us alive, but it makes astronomy really, really annoying. The atmosphere does a lot of good things. It gives us air to breathe, it protects us from harmful radiation, It makes life possible. But for astronomers, it's the equivalent of trying to watch a movie through a stained glass window that someone keeps jiggling. Everything shimmers, everything blurs. The atmosphere absorbs certain wavelengths of light entirely, blocking entire portions of the electromagnetic spectrum from ever reaching your instruments. In 1946, a scientist named Lyman Spitzer had an idea, and like many great scientific ideas, it sounded completely insane at the time. Spitzer proposed putting a telescope in space, not a small telescope, not a toy, a serious astronomical observatory, orbiting above Earth's atmosphere, with an unobstructed view of the cosmos. He wrote a paper about it, lobbied for it, spent decades advocating the concept, and nobody took him seriously for 20 years. Why? Well, because in 1946 we couldn't even put a human into space. The idea of launching a delicate precision scientific instrument into orbit seemed about as realistic as suggesting we colonize Mars, using only balloons and dreams. But Spitzer kept pushing. He refined his proposals, found allies, and gradually the technology began to catch up with the vision. The launch pad at Cape Canaveral, Florida, October 1968. A Titan 3C rocket roars to life, carrying into orbit a satellite that would change astronomy forever. It's called the OAO-2, the Orbiting Astronomical Observatory 2. It was humanity's first successful space observatory, a proof of concept that proved, against all odds, that Spitzer's crazy idea was actually going to work. OAO-2 carried two ultraviolet telescopes, and it operated for nearly 4 years, observing stars, nebula, and galaxies, with a clarity that ground-based telescopes couldn't match. Ultraviolet light, previously almost entirely blocked by Earth's atmosphere, flooded into its instruments. Scientists have been working in essentially mittens their entire careers. OAO-2 was like giving them surgical gloves for the first time. The age of space observatories had begun. Development. OAO-2 was just the beginning. Once NASA and the international scientific community realized that space-based astronomy wasn't just a fantasy, the race was on to build something bigger, better, and more ambitious. The 1970s brought a string of missions, each pushing the boundaries further. The Copernicus Observatory, the International Ultraviolet Explorer, the Einstein Observatory, which gave us our first X-ray images of the cosmos. Because here's something fascinating. Different wavelengths of light reveal completely different things about the universe. Visible light shows us stars and galaxies. Infrared shows us dust clouds and newly forming stellar systems. X-rays show us violent, energetic events. Black holes consuming matter, neutron stars colliding, the cosmic equivalent of a mosh pit. Ground-based telescopes could only access a tiny slice of this electromagnetic buffet. Space observatories opened up the entire restaurant. Yes, I realize I'm mixing my metaphors here. The point is, the universe is a lot more interesting when you can see all of it, not just a tiny bit that happens to wiggle through our atmosphere. But the crown jewel of this era, the telescope that would define a generation and become arguably one of the most famous scientific instruments in human history, was conceived in 1979 and launched in 1990. The Hubble Space Telescope. Now here's a fun fact that non-astronomy people often don't know. Hubble launched with a flaw, a massive, embarrassing, almost catastrophic flaw. The mirror had been ground to the wrong shape, only by about 1/50th of a human hair. This does sound small, but in telescope terms, it was catastrophic. Images came back blurry. The press had a field day. Newspapers ran headlines calling it the Hubble headache and the billion-dollar blur. But NASA's response is why we remember Hubble as a triumph rather than a disaster. They sent astronauts to fix it. In 1993, the Space Shuttle Endeavour carried up a crew to install corrective optics, like giving the telescope a pair of glasses. And it worked. Beautifully. Spectacularly. Over the next 3 decades, Hubble would produce images that changed how humans see the universe. The Pillars of Creation, the Hubble Deep Field, which revealed that every single point of light in a seemingly empty patch of sky is actually a galaxy containing hundreds of billions of stars. The evidence the universe is accelerating in its expansion, leading to the discovery of dark energy. Hubble was designed for a 15-year mission. It lasted 32. And even now, after its final service mission, it just keeps chugging along, sending back data, expanding our cosmic horizons. But as good as Hubble was, it was limited. It was designed in the 1970s and built with 1980s technology. And as impressive as its images were, there were questions it simply couldn't answer. Questions that would require something much bigger, something more powerful, something that could see further back in time than any telescope in history. That brings us to the present day and the undisputed heavyweight champion of space observatories. But before we get to the good stuff, just a quick note. If you're enjoying this journey into the cosmos, make sure you subscribe to What Is and hit that notification bell. Now back to the largest, most powerful space telescope ever built. The largest and most prominent. December 25th, 2021, Christmas morning. A rocket lifts off from French Guiana, carrying a payload that represents the combined ambitions of NASA, the European Space Agency, and the Canadian Space Agency, the James Webb Space Telescope. Let me give you some numbers to appreciate the scale of this thing. Webb's primary mirror is 6.5 meters in diameter. That's about 21 feet across. That's roughly the length of a tennis court. The mirror is made up of 18 separate hexagonal segments, each coated with a thin layer of gold, because gold reflects infrared light extremely well. If you extracted all the gold used in Webb's mirror, you'd get about as much as you'd find in a small trophy. But that tiny amount, painstakingly applied, makes each segment reflect 98% of the light that hits it. The sun shield alone, this big, multi-layer sheet that keeps the telescope cold and shaded, is the size of a tennis court. It has 5 layers, each as thin as a human hair, and when Webb was launching, the entire thing had to be folded up like origami to fit inside the rocket's nose cone. What makes Webb so revolutionary, unlike Hubble, which operated primarily in visible and ultraviolet light, Webb is designed to see in infrared. This is crucial for several reasons. First, infrared light can penetrate dust clouds that block visible light. When you look at a nebula in visible light, you're often looking at dark, murky patches. In infrared, you can see the stars forming inside, cocooned in the very dust that hides them from our view. Second, and this is a truly amazing part, Webb can see the light of the first galaxies that formed after the Big Bang. This is because the universe is expanding. Light from those ancient objects has been stretched. That's right, stretched. By its journey across billions of years. Visible light becomes infrared. The further back we look, the redder things get, until they finally fade into the infrared spectrum entirely. Ground-based infrared telescopes exist, but they have a problem. Everything emits infrared light, including the telescope itself, the atmosphere, and nearby warm objects. To do infrared astronomy, you need your telescope to be incredibly cold. Cold enough that its own heat doesn't swamp the faint signals from distant galaxies. Webb achieves this through that enormous sun shield, which keeps the instruments at about minus 233 degrees Celsius. That's colder than any natural temperature on Earth, colder than Pluto on a warm day. When engineers were testing Webb on Earth, they had to account for the fact that human breath contains enough moisture to frost over the mirror. so they built clean rooms with elaborate air filtration systems. Astronauts wore what looked like full-body diapers, not because of any bathroom situation, but because even the moisture from a single bathroom break could damage the mirror. Webb orbits the Sun, not Earth. It's parked at a point called Lagrange Point 2, about 1.5 million kilometers from Earth. This location was carefully chosen. It's stable, meaning Webb uses minimal fuel to stay in position, and it's far enough away from Earth that our planet's heat and infrared emissions don't interfere with the observations. The trip there took 6 months. Once it arrived, mission controllers spent another 6 months unpacking, unfolding, and calibrating everything. Every solar panel had to be deployed correctly. Every mirror segment had to be alignment checked and adjusted to within a fraction of a wavelength of light. And then it opened its eyes. What are they looking for? So Webb is operational. It's in position, its mirrors are aligned, its instruments are cooled, and it's taking images that make astronomers weep with joy. But what is it actually looking for? What's on the scientific shopping list for the most expensive telescope ever built? The science goals fall into several major categories, and each one represents one of the biggest questions in modern astronomy. First up, the early universe. Webb is designed to observe objects that formed in the first few 100 million years after the Big Bang. This is an epoch we've never directly seen. We've had theories about how the first stars and galaxies formed, but we've never had a telescope capable of testing those theories. The light from these objects has been traveling for 13 billion years, stretched into the infrared, incredibly faint and easily confused with other nearby objects. Webb's infrared vision and massive mirror make it uniquely capable of piercing this cosmic fog. Already, within months of first light, it has found galaxies that shouldn't exist by our previous models. Massive, mature galaxies that seem to have formed too quickly after the Big Bang. This is the kind of problem astronomers love. Not a crisis, but an invitation to revise our understanding. Second target, exoplanets. That's the term for planets orbiting stars other than our Sun. Since the first confirmed detection in 1995, we've discovered over 5,000 exoplanets. Most are giant gas planets like Jupiter and Saturn, because big planets are easier to detect. But as our techniques have improved, we've started finding smaller, rockier planets in the habitable zones of their stars. Not too hot, not too cold, where liquid water could exist on its surface. Webb isn't designed to take pictures of these planets directly, not usually anyway. Instead, it analyzes their atmospheres. When a planet passes in front of a star, some of the starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths of light, leaving a chemical fingerprint. Webb's instruments can read those fingerprints, detecting water vapor, carbon dioxide, methane, and potentially even signs of biological activity. Is there life out there? Webb won't answer that question definitively, but it will tell us which worlds are worth investigating further, which atmospheres look like they might be doing something interesting. Third major category, stellar life cycles. We understand the basics. Stars form from collapsing clouds of gas and dust. They spend most of their lives fusing hydrogen into helium. They die in different ways depending on their mass, peacefully for small stars, cataclysmically for large ones. But the details are murky. How exactly do stars push the leftover material back into space to seed a new generation of stars? What happens inside a nebula where dozens of stars are forming simultaneously? Webb's infrared vision cuts through the dust to reveal these stellar nurseries in unprecedented detail. And then there's the weird stuff. Webb has observed the collision of two neutron stars, an event that creates half the heavy elements in the universe. It's watched a black hole devour a star, an event called a tidal disruption. It's looked at Jupiter and found unexpected features in its atmosphere. It's examined the atmospheres of planets in our own solar system with instruments that would have seemed like science fiction just a generation ago. But for all its capabilities, Webb isn't the end of the story. It's not even the only game in town. The future. The history of space observatories is a story of constantly pushing outward. Each generation builds on what came before, answering some questions while revealing entirely new mysteries. So what's next? Several major missions are already in development. The Nancy Grace Roman Space Telescope, named for the pioneering astronomer, is currently, at time of recording, scheduled for launch in late 2026. It's designed for wide-field infrared surveys, capable of mapping large swaths of the sky with Hubble-quality resolution. Roman will hunt for exoplanets, study dark energy, and potentially discover entirely new phenomena, simply by observing at scales we haven't yet explored. On the ground, the extremely large telescope is being built in Chile, with a mirror 39 meters across. That's larger than a basketball court. Ground-based telescopes will never match the clarity of space observatories, but they can be built much larger and updated more easily. The next generation of ground-based giants will work in concert with space telescopes, providing complementary capabilities. China is constructing the Jiutian Space Telescope, which will have a field of view 350 times larger than Hubble, allowing it to map huge portions of the sky. India has expressed ambitions for its own space observatory missions. Private companies are discussing space-based telescopes that could be built more cheaply and launched more rapidly than traditional government missions. But perhaps the most exciting developments aren't about any single telescope. They're about the conversions of capabilities that will allow us to finally answer questions we've been asking for centuries. Direct imaging of exoplanets, not infrared from wobbling stars or dimming lights, but actual pictures of worlds around other stars. Several missions in development aim to do this, blocking out the glare of the parent star to reveal the faint reflected light of planets. Gravitational wave detection from space. Ground-based detectors like LIGO have revolutionized our understanding of black holes, but they are limited to the most violent collisions. A space-based gravitational wave observatory could hear the gentle whispers of supermassive black holes merging, potentially taking us back to the first moments after the Big Bang. Studying the nature of dark matter and dark energy, these phenomena make up 95% of the universe, and we still don't understand what they are. Future space observatories will map the distribution of dark matter through gravitational lensing, and measure the expansion of the universe with unprecedented precision. And always, always looking deeper into the early universe. Webb can see the first galaxies. What comes after will see the first stars, and perhaps, eventually, the cosmic dark ages before any light existed at all. This is the great adventure of our species. Every space observatory, from OA02 to Webb and beyond, represents humanity's collective effort to understand our place in the cosmos. So what is a space observatory? More than a telescope in orbit, more than a scientific instrument. It's an extension of human curiosity, a way of seeing that transcends the limitations of our home planet. We built OA02 because Lyman Spitzer refused to accept that the atmosphere had to be a permanent wall between us and the universe. We built Hubble because we wanted to see clearly. We built Webb because we wanted to see further, deeper, and in wavelengths we couldn't previously access. And we'll keep building them because the universe keeps revealing new layers of complexity, beauty, and mystery. If you found this journey through the cosmos fascinating, hit that like button. For more content that breaks down the biggest questions in science, space, and human knowledge, subscribe if you haven't already. Because here's the thing about exploration. It never ends. Every answer generates new questions. Every horizon once crossed reveals another beyond. The universe doesn't care if we're confused. It just keeps expanding, evolving, and existing on scales that make our existence seem brief and improbable. And yet here we are, a species of hairless primates barely 300,000 years old, building telescopes that can see back to the very beginning of everything. That's remarkable. That's worth celebrating, and that's absolutely worth subscribing for. Until next time, keep looking up and keep asking what is. See you next time. You're standing on a beach. You've got a handful of sand. And I'm going to tell you that in about 30 million years, or roughly 3 weeks if you've got a really good kiln, that handful of sand could become the window that you're looking through right now. That's glass. And today we're going to answer a question that has kept humanity awake since someone first accidentally melted sand. What is glass, and how does sand become transparent? Welcome to What Is, the channel where we take the everyday things you completely ignore and make you appreciate them just enough to impress people at parties. Today's topic, glass. The stuff you drink out of, the stuff you look through, the stuff your phone screen is made of, which you're currently staring at instead of making eye contact with other people. Let's dive in. 1. How it works, the science. First things first, what is glass? And here's where things start to get weird, because the scientific answer is glass is a solid, but not really. It's also a liquid, but also not really. It's what scientists call an amorphous solid, which is just a fancy way of saying we gave up trying to classify it. Here's the deal. Most solids like ice, metal, or that questionable leftover pizza in your fridge have molecules arranged in a nice orderly crystal lattice. They're organized, they're predictable, they're boring. Glass molecules, they just don't care. They're all arranged willy-nilly, like people standing in a queue at a grocery store when there's no actual line. This disorganized arrangement is why glass is transparent. The light waves pass through it, they don't get bounced around in a predictable way. They just sort of slide through. The atoms in glass don't absorb visible light in the way that other materials do. Instead, they let it pass right on through. Think of it like this. Regular solid matter is a crowded nightclub where photons can't get to the dance floor. Glass is the VIP section where light just walks straight in. Now here's where I get personally jealous. I've been trying to achieve transparency my whole life. I put on clothes and people see clothes. I put on a shirt that says I'm transparent, and people definitely see that shirt. Meanwhile, glass is out there just existing, literally just sitting there, and light is like, yeah, I'll pass right through that. Unfair. But let's talk about sand, because that's where the magic really starts. Sand is mostly made up of silicon dioxide, SiO2 for those who speak chemistry. Those are silicon atoms bonded to oxygen atoms, forming little triangular shapes. They're actually pretty stable, fairly boring molecules. But here's the key. Silicon dioxide has an extremely high melting point, like 3,100 degrees Fahrenheit high. That's hot enough to melt steel. That's hot enough to make the devil himself sweat. So how do we actually turn sand into glass? Well, we cheat. See, pure silicon dioxide is super stubborn, but add in some soda ash, also known as sodium carbonate, and you drop that melting point to something a bit more manageable, like 1500 degrees Fahrenheit. It's still obscenely hot, but now we're in the realm of industrial furnace rather than science fiction volcano. Once you heat that mixture up, the silicon and the oxygen bonds start to break apart. The soda interferes with the crystalline structure formation, and when you cool it back down fast, really fast, you get that distorted molecular arrangement we talked about. The rapid cooling is crucial. If you cool it down too slow, the molecules have time to organize into crystals, and you get ceramic. Nobody wants ceramic windows. Well, some people do, but that's for a different video. Fun fact, there's no official chemical formula for glass. Scientists have tried to write one, and they failed. Glass as a substance is essentially we'll know it when we see it. It's a bit like asking what is the recipe for a mess. You can describe the elements of it, but there's no single formula. I've never related to something more in my life. 2. Origins. Now let's talk about the origins. And this is where glass gets really interesting. Humans have been making glass for about 4,500 years. The earliest known glass objects were tiny beads found in Egypt, dating to around 3,500 BCE. These weren't transparent, they were opaque, coloured, and probably accidentally created during metal work. The ancient Egyptians were actually fantastic at glass making, but they kept their methods super secret. Like will kill you if you tell anyone's secret. This led to centuries of people thinking glass was some mystical Egyptian art form that couldn't be replicated. It could, they just wanted you to think that it couldn't. Then came the Phoenicians, who legend says discovered glass by accident, when their campfires on beach sand got hot enough to melt the silica. This may or may not be true, but it's a great story, so we're keeping it. The real revolution came with the Romans. Around 100 BCE, someone in Syria invented glass blowing, and suddenly glass went from precious treasure for the elite to we can make cups for everyone. Roman glasswork was actually remarkably advanced. They made window glass, mirrors, drinking vessels, even glass fake eyes, because apparently vanity is a timeless human trait. The Romans also discovered that adding certain minerals created different colors. Add a tiny bit of gold and you get a ruby red glass. Add copper, blue-green. Add manganese, violet. They were essentially playing with chemistry before chemistry existed. I can barely play with recipe ingredients without accidentally creating something that kills plants. Meanwhile, ancient Romans, let's add some crushed up bones and see what happens. And it worked. Incredible. The Middle Ages gave us stained glass, primarily because the Catholic Church wanted to make buildings look even more like heaven, so people would donate more money. It worked beautifully. Those massive cathedral windows, not actually made of clear glass, they're loaded with metallic oxides that create colors, but the tech eventually evolved to produce clearer glass, which brings us to the modern times. Here's a fun modern fact that will make you appreciate your windows. The primary method used for making clear glass today is called the float process, invented in the 1950s by Sir Alistair Pilkington. You float molten glass on top of molten tin. The glass flattens out perfectly due to gravity and surface tension. No rolling pins required. No smoothing necessary, just physics doing its thing. This one innovation is why window glass got to be so cheap. Before the float process, making flat glass was a nightmare of grinding and polishing. Now, floating, on tin, like some beautiful metallic pool party for molecules. Alright, we're about 7 minutes in, and if you made it this far, congratulations. You know more about glass than most humans alive. Give yourself a pat on the back, or a high five. I'm behind a microphone, I can't high five without messing up the audio, but I believe in you. And if you're new here, this is the part where I remind you that there's a subscribe button with my name on it. Well, actually, it's the channel's name. Either way, subscribe. We do videos like this every day. Anyway, back to glass. 3. Types and uses. Not all glass is created equal. Turns out sand and soda and heat equals basic glass. But if you start messing with the recipe, you get some wild stuff. Let's run through some of the highlights. First up, tempered glass. This is safety glass, heat treated to be stronger than regular glass. When it breaks, it shatters into small, relatively harmless pieces, instead of massive slashing shards. Your car windows, tempered. The side and rear windows specifically. The windshield is laminated. 2 layers of glass with plastic in between them so it holds together when broken. Your phone screen is also probably tempered, which is why it survives the occasional floor encounter, but not your keys plus phone in pocket situation. That one's on you. Next, borosilicate glass. This is the fancy stuff. Glass with boron added. It's extremely heat resistant and chemically stable. If you've ever seen a science movie with weird glass tubes and beakers, that's borosilicate. It doesn't expand much when heated, so it won't crack when you pour boiling water into it. It also won't shatter when you look at it menacingly. Good glass. Pyrex cookware, that's borosilicate. Your grandmother's famous casserole dish that survived being dropped on Thanksgiving. Borosilicate. Meanwhile, I can't survive being looked at too aggressively. Different glass, different vibes. Now here's where it gets insane. Fiber optics. Glass can be drawn into fibers thinner than the human hair. These fibers can transmit information as light, pulses of light shooting through glass threads at insane speeds. All the internet data flowing through the world's undersea cables, glass fibers. Every video you're watching on your phone right now probably traveled through glass at some point, and for this video, it's certain as I use a fiber connection to upload videos. The entire modern telecommunications infrastructure is just very fancy sand. Then there's Gorilla Glass, developed by Corning specifically for electronics. This stuff is chemically strengthened, extremely scratch resistant, and designed to survive the chaos of daily human life. Modern smartphones use variations of this. Your screen is essentially a thin sheet of engineered sand that can resist your keys, your coins, and your desperate attempts to remove the screen protector without bubbling. I love Gorilla Glass. It's the one type of glass I can genuinely relate to, constantly being asked to endure more than it was designed while maintaining a calm, transparent exterior. Glass fiber, also called fiberglass, is glass spun into tiny threads and woven into insulation. It traps air in millions of tiny pockets, making it one of the most effective insulation materials on the planet. Your house probably has fiberglass insulation. Every time you turn on your AC and marvel at how comfortable you are, you're thanking sand. Sand that was melted, spun into threads, and turned into fluff. Honestly, it's kind of beautiful. And let's not forget optical glass. Lenses for eyeglasses, cameras, microscopes, telescopes. This is special high purity glass designed to bend light in a very precise way. The Hubble Space Telescope's main mirror was initially the wrong shape due to a manufacturing error. It cost millions to fix, but they were able to fit the telescope with glasses, well, more of a monocle. And it worked. That's optical glass for you. You gotta get it exactly right, or suddenly you're seeing the universe blurry. Fun fact, the average person touches glass over 400 times a day. Phone, coffee cup, window, car, computer screen, refrigerator door. You're basically in a committed relationship with sand, and you didn't even know it. I touch glass maybe 1,000 times a day, and I'm still single. Life is confusing. So let's bring this all together. Glass is essentially sand that got hot enough to forget its crystalline structure, cooled down fast enough to stay confused, and now lets light pass through it like it's got nothing to hide. It's been with us for 4,500 years. It built empires through windows and mirrors. It connects the entire world through fiber optics. It protects your phone, heats your home, and helps scientists see things on the edge of the universe. And it all starts with sand, the most abundant thing on Earth's beaches, just sitting there looking useless, waiting for someone to get it hot enough to become something extraordinary. Next time you're looking through a window, or drinking from a glass, or staring at your phone screen because you're avoiding something else, you're looking at transformed sand. You just witnessed a 30 million year or 3-week transformation happening right in front of you. I think that's kind of beautiful. And that was how sand becomes transparent. This has been What Is, taking ordinary things and making them just interesting enough to tell your friends about. If you learned something new, hit that like button. If you learned nothing, hit that like button. I'm trying to hit algorithm milestones here. And subscribe too. It really helps the channel grow. I'll see you in the next one. Now go outside and look at some glass. You've earned it. Imagine you're standing in front of two identical looking cars. Same size, same color, same shiny rims. One of them has a yellow sticker on the windshield that says diesel. The other has a similar sticker that says petrol. Now here's the $1 million question. Why does one of them sound like it's trying to murder you every time it starts, while the other purrs like a kitten designed by accountants who've never heard the word excitement? Or wait, maybe I've got it backwards. Maybe the diesel is the quiet one, and the petrol car is the one that screams like a teenager who's just discovered heavy metal music. Welcome, friends, to one of the most confusing debates in automotive history. Today we're going to answer a question that has baffled humanity since the dawn of the internal combustion engine. Well, not quite the dawn exactly, The diesel engine came a bit later, but we'll get to that. I'm going to teach you everything you need to know about diesel and petrol engines. Not just the basics, but the really interesting stuff. The kind of facts that will make you the most fascinating person at your next dinner party. Assuming your dinner parties are attended by people who unironically say things like, "Oh, interesting, you know about compression ratios?" By the end of this video, you'll understand exactly what makes these engines different, where they came from, why we use both of them, and what the future holds. Plus, I'll throw in some jokes because apparently the algorithm rewards engagement, and my mortgage payments depends on you lovely people watching till the end. So let's begin, shall we? Well, first, if you're new here, welcome to What Is, the channel that answers the questions you never knew needed answered. We're like that friend who knows a little bit about everything and won't stop talking about it. Consider subscribing. It's free, unlike my student loans. Let's start off with the origins. Every great story has a beginning, and the story of the internal combustion engine begins in the most German way possible, with a man named Nicholas Otto. No, that's not a typo. This Nicholas, born in 1832 in Holzhausen, Germany, wasn't related to the Tesla fellow, despite what the confusion in your head might suggest. Otto was an engineer who in 1876 built the first practical four-stroke internal combustion engine. We call it the Otto cycle to this day, which sounds like either a roller coaster or a painful medical procedure, depending on your perspective. Now here's where it gets interesting. Otto's engine ran on something called town gas, which is exactly what it sounds like. Gas made from coal that cities would produce and distribute like, well, city gas. It wasn't very efficient and it wasn't very portable, but it worked. Sort of. Like a car that only breaks down 3 times before making it to the store. Then came Gottlieb Daimler and Carl Benz. Yes, that Benz. The one with the fancy car brand. These two geniuses figured out how to make petrol, which is just gasoline refined from petroleum, actually run an engine properly. By 1886, Benz had patented the first true automobile, and Daimler had created the first four-wheeled vehicle powered by a high-speed petrol engine. Meanwhile, across the channel in England, a clerk named Frederick Winslow Diesel was having what I can only assume was a series of very stressed thoughts about efficiency. Diesel was born in Paris in 1858 to German parents, and he was obsessed, and I mean obsessed, with the idea of creating an engine that could compete with steam power without all the hassle of boiling water and waiting around. Steam engines, you see, were wonderfully efficient in theory, but absolutely terrible in practice. They required huge boilers, lots of fuel, lots of water, and lots of patience. Diesel's breakthrough came from a deceptively simple question. What if we didn't need spark plugs at all? In 1892, Diesel filed his patent for a rotational heat motor that worked by compressing air so tightly that it got hot, really hot, and then when fuel was introduced to this superheated air, it would ignite on contact. No spark needed, just compression, heat, and boom. Well, not boom exactly. That's the petrol engine's speciality. More of a controlled whoosh. The first practical diesel engines were massive things. Too big for cars, mostly used in factories and ships. It wasn't until 1936, nearly 40 years after Diesel's patent, that Mercedes-Benz built the first diesel-powered passenger car, the 260D. And even then, diesel cars remained a niche market, popular mainly among taxi drivers who appreciated the fuel economy, and people who wanted their neighbors to know exactly when they were leaving for work. But what about petrol engines? Well, they had nearly a 50-year head start. By the time diesel cars were becoming practical, petrol engines had already conquered the world. Henry Ford's Model T, introduced in 1908, ran on petrol, and became the first automobile that normal people could actually afford. The combination of petrol's energy density, the relative simplicity of spark ignition, and Ford's manufacturing genius created a perfect storm that made petrol the obvious choice for personal transportation. For nearly a century, petrol reigned supreme. Diesel lingered in the shadows. Trucks, trains, ships, and the occasional eccentric millionaire's luxury car. They coexisted like two species in the same ecosystem, each occupying its own niche, neither really competing with each other. But why? What makes them so different? That's what we're going to explore next, and believe me, the differences are fascinating. The key differences. Alright, pay attention, because this is the good stuff. The stuff that separates people who understand engines from people who just put gas in them and hope for the best. The fundamental difference between diesel and petrol engines comes down to 3 words: compression, ignition, and explosion. Yeah, well, that's actually 4 words if you count the ands separately, but let's not get pedantic. Let's start with the petrol engines because they're actually more complicated in a counterintuitive way. A petrol engine works by drawing in a mixture of air and fuel, compressing it to about 1/10 its original volume. Compression ratios typically range from 8:1 to 12:1, and then, right at the peak of compression, a spark plug fires. That spark ignites the mixture, creating a controlled explosion that pushes the piston down, converting chemical energy into mechanical energy. It's elegant in a way, a tiny controlled explosion, perfectly timed, happening hundreds of times a minute. The engine's computer, or in older cars, a distributor, decides exactly when to fire the spark and get the best power and efficiency. It's like conducting an orchestra, where every instrument is a tiny controlled explosion, and the conductor is a computer that can make decisions in milliseconds. Diesel engines, on the other hand, don't mess around with spark plugs. Zero, zip, nothing. The diesel approach is pure, brutal efficiency. Air is drawn into the cylinder and compressed to a much higher ratio, typically between 14:1 and 25:1, sometimes even higher. This extreme compression heats the air to a temperature around 1000 degrees Fahrenheit, which is roughly the temperature of a pizza oven, and significantly hotter than you want your car engine to be under normal circumstances. At the precise moment when the air is superheated, fuel is injected directly into the cylinder. Because the air is so hot, the fuel ignites immediately upon contact. No spark needed. No carefully timed electrical discharge, just compression, heat, and pure chemistry of diesel fuel meeting superheated air. This is why diesel engines are so robust. There are no spark plugs to gap, no ignition coils to fail, no distributors to wear out. The fuel system does all the work. And if you've ever priced a diesel fuel injection system, you can confirm that all the work comes with an appropriately large price tag. Now here's where things get really interesting, and where most people get confused. Petrol engines are designed to prevent unexpected ignition. The fuel-air mixture in a petrol engine is carefully calibrated to burn cleanly and predictably when sparked, but not to ignite spontaneously from heat and pressure. If petrol auto-ignited from compression alone, the engine wouldn't work properly. You'd have random explosions happening in the wrong times, which is bad for longevity, and also not exploding. Diesel fuel, by contrast, wants to ignite. It's specifically formulated to have high auto-ignition temperature, in the context of a controlled ignition, meaning it waits patiently in the fuel line until it's injected into the superheated air, at which point it enthusiastically combusts. The cetane rating of diesel measures how quickly it ignites, like an octane rating, but for diesel, and in the opposite direction. High cetane means quick ignition, which is desirable. But wait, there's more. And by more, I mean the elephant in the room, that everyone notices but nobody can quite articulate. The sound. Diesel engines are loud. There's no diplomatic way to say this. From the moment you start a diesel engine, it announces its presence to the entire neighborhood. Like that neighbor who plays the acoustic guitar at 7 a.m. Why are you doing that? It comes down to the rate of combustion. In a petrol engine, the spark ignites the mixture, and the flame front spreads relatively slowly across the combustion chamber. It's a gentle, controlled burn. In a diesel engine, when fuel is injected into the superheated air, it ignites everywhere at once. The injection process itself creates a bit of a shockwave. The combustion happens faster and more violently. This rapid pressure rise creates that characteristic diesel clatter, especially at idle. Modern diesel engines have gotten much quieter through careful engineering, better fuel injection systems, sound dampening materials, and refined combustion chamber designs. But they'll never be as quiet as petrol engines. It's physics. You can't change the laws of physics. You can't fight physics and win. Unless you're building a Formula One engine, in which case you're fighting physics and everyone's impressed. Another key difference involves weight and power density. Diesel engines are typically heavier than petrol engines of equivalent power because they need thicker walls to handle the higher compression ratios and the resulting pressures. This makes diesel engines great for applications where durability matters more than weight, like ships, trucks, and heavy machinery, and less ideal for applications where every pound matters, like sports cars and aircraft. Petrol engines with their lower compression ratios and spark ignition systems can be built lighter and rev higher. That's why your average sports car engine revs to 7,000 or 8,000 RPM, while most diesel engines are lucky to see 4,500. It's not that diesel engines can't rev high, it's that the design constraints make it impractical and expensive. Fuel economy is where diesel traditionally shined. Because diesel fuel has about 12% more energy per gallon than petrol, and because diesel cycles are more thermally efficient, a diesel engine would typically achieve 25 to 30% better fuel economy than an equivalent petrol engine. This is why over-the-road trucks are almost exclusively diesel, and why European drivers historically preferred diesel for highway driving. But, and there's always a but, modern petrol engines have closed much of this gap through direct injection, turbocharging, and other technologies. A new efficient petrol engine might achieve diesel-level fuel economy in everyday driving, removing one of diesel's traditional advantages. Finally, there's the matter of cold weather. If you've ever lived somewhere cold and owned a diesel vehicle, then you know that special joy of diesel fuel turning into something resembling candle wax overnight. Diesel has a higher cloud point and pour point than petrol, meaning it thickens and solidifies at higher temperatures. This is why diesel vehicles need block heaters in cold climates, and why you sometimes see lines at diesel stations in winter as people hope for the summer blend to arrive. Petrol, by contrast, behaves nicely in cold weather because its components are more volatile. It doesn't want to turn to wax at the slightest dip in temperature. This is one of the quietly practical reasons why petrol remains popular in colder regions. Current roles. Now that we understand how these engines work, let's talk about where they actually live in the world today. Because despite what certain internet arguments might suggest, there's actually a pretty sensible division of labor between diesel and petrol engines. It's almost like engineers, over more than a century of experimentation, figured out which tool works best for which job. Let's start with diesel, since we've been talking about it. Where does diesel reign supreme? Heavy-duty transportation is diesel's kingdom, and it will remain so for the foreseeable future. Every semi-truck you see on the highway, every train locomotive that isn't electric, every large ship crossing the ocean, these almost all run on diesel. Why? Torque. Torque is the twisting force that gets heavy things moving. Diesel engines produce massive amounts of torque at low RPMs. A modern semi-truck engine might produce 2,000 pound-feet of torque, which is enough to tow a small building, and it does it while idling around 600 RPM, barely ticking over, sipping fuel the way a reasonable person sips water after running a marathon. Petrol engines, by contrast, need to rev higher to produce their maximum torque. A high-performance petrol engine might hit peak torque at 4,000 or 5,000 RPM, which is great for zooming around in a sports car, but terrible for hauling 40 tons of freight. You can't shift an 18-speed transmission at 7,000 RPM. Well, you can, but your driver will quit. Construction equipment is almost entirely diesel for similar reasons. Excavators, bulldozers, loaders, and cranes need massive low-end power and durability to run for thousands of hours with minimal maintenance. Diesel excels at both. When you're digging a foundation for a skyscraper, the last thing you want is an engine that needs premium fuel and spark plug replacements every 500 hours. Agricultural machinery follows the same logic. Tractors, combines, and harvesters all benefit from diesel's combination of torque, durability, and fuel efficiency. Modern tractors can cost more than a luxury house, but they're expected to run for decades, with proper maintenance that is. Diesel isn't a choice here. It's practically the only sensible option. Passenger vehicles are where things get complicated. In Europe, diesel passenger cars represented around 50% of new sales as recently as 2015. The appeal was simple: better fuel economy, lower CO2 emissions per mile, and diesel's reputation for lasting forever. European countries tax diesel fuel more lightly than petrol, making it economically attractive. But then, as they say, things happened. The Volkswagen emissions scandal of 2015 revealed that numerous diesel cars were cheating on emissions tests, producing up to 40 times the legal limit of nitrogen oxides in real-world driving. This shattered public trust in diesel vehicles, practically overnight. Combined with increasingly stringent emission standards and the rise of hybrid technology, diesel passenger car sales collapsed across Europe, falling to around 15 to 20% of new car sales by the early 2020s. In the United States, diesel passenger cars never really caught on. American consumers, raised on cheap petrol and wide open spaces, preferred larger vehicles with petrol engines. Dodge Rams, Ford Escalades, not Volkswagen TDIs. The few diesel passenger cars sold in America were niche products for enthusiasts who appreciates their efficiency and torque, people willing to pay a premium and accept certain compromises. As of this recording, the future of passenger car diesel is uncertain. New emission regulations in Europe and elsewhere make it increasingly expensive to produce compliant diesel engines, and the business case for developing a new platform becomes harder to justify. Major manufacturers are quietly phasing out diesel passenger cars, with plans to discontinue most or all of them by the early 2030s. So where does petrol reign? Pretty much everywhere else. The light-duty vehicle market, cars, SUVs, pickup trucks, minivans, it's overwhelmingly petrol-powered. Petrol engines are quieter, smoother, cheaper to manufacture, and perfectly adequate for the needs of most drivers. When you rent a car at the airport, you're almost certainly getting a petrol engine, unless you've specifically requested otherwise, and the rental company might not even offer that as an option. Small aircraft piston engines are almost universally petrol-powered. This might surprise you if you are expecting aviation to be more sophisticated, but the reasons are practical. Petrol engines are lighter for equivalent power, which matters enormously in aircraft. They're also simpler to maintain and operate, which is important when you're 5,000 feet above the ground and something goes wrong. Lawn equipment, motorcycles, scooters, snowmobiles, personal watercraft. Basically anything that needs a small internal combustion engine runs on petrol. The reasons are cost, weight, and noise. A small diesel engine would be prohibitively expensive and heavier than the equivalent petrol engine, and nobody wants to hear a lawnmower that sounds like a container ship. High-performance applications still favor petrol, but this is changing. Electric motors are now delivering supercar-level performance without any engine noise at all, which makes the traditional engine wars somewhat moot. A Tesla Model S Plaid will beat almost any petrol supercar in a straight line, and it does it without any combustion at all. But we'll get to the future in a moment. In fact, we'll get to the future now. We've talked about where these engines came from and where they're used today. Now let's address the question that everyone's thinking about but no one wants to ask out loud. Are diesel and petrol engines going to disappear? The short answer is sort of, gradually, in certain applications. It's complicated. Let's start with a prediction that will almost certainly be wrong. Internal combustion engines will still be around in 50 years. Probably. There will be edge cases. Specialized applications, collector vehicles, hobbyist projects, developing nations with less infrastructure, where petrol and diesel engines will continue to exist. The engine isn't dead, it's just no longer the only game in town. The passenger car market is where the most dramatic changes are happening. Governments around the world announce bans or severe restrictions on new petrol and diesel car sales within the next 10 to 20 years. The United Kingdom will ban pure petrol and diesel cars by 2030. France and Germany have similar targets around 2035. California, that regulatory trendsetter, has set 2035 as the deadline for new zero-emissions vehicles. These regulations are pushing manufacturers towards electric vehicles at a pace that would have seemed impossible just 5 years ago. Volvo, Mercedes, BMW, Audi, Volkswagen, General Motors, and Ford have all announced plans to transition to largely or entirely electric vehicles over the next decade. Some, like Volvo, aim to be fully electric by 2030. What does this mean for petrol engines? It means their end is probably in sight for passenger cars. The internal combustion engine's 130-year reign as a dominant automotive power source will likely end within the lifetime of people watching this video. That's genuinely historic. It's like watching the transition from horse to car, except this time it's the car being replaced by something else. But, and you knew there was going to be another but, heavy-duty transportation is a different story. Electrifying semi-trucks is much harder than electrifying passenger cars. Batteries are heavy, and heavy batteries reduce payload capacity, which directly impacts the economics of freight. A fully loaded semi-truck might need thousands of kilowatt hours of battery capacity to achieve practical range, and that battery would weigh tens of thousands of pounds. Hydrogen fuel cells offer an alternative, and companies like Toyota and Hyundai are investing heavily in fuel cell trucks. But hydrogen infrastructure is essentially non-existent, and the physics of hydrogen storage create their own challenges. The realistic forecast for heavy-duty transport is a gradual transition over several decades, with diesel remaining dominant for long-haul applications well into the 2040s or beyond. Trains, ships, and aircraft will follow similar trajectories, longer timelines than passenger cars, but movement towards alternatives. What about the hobbyists? What about the millions of people who love cars, work on engines, and find genuine joy in the sound and smell of internal combustion? They'll be okay, for a while at least, hopefully. Classic cars are already exempt on many emissions regulations, and there's a thriving community around preserving and restoring older vehicles. Motorsport will continue with internal combustion engines for the foreseeable future, as racing series like Formula One and NASCAR transition slowly, or not at all. The enthusiast community is small but passionate, and they'll keep these engines alive long after the automotive industry has moved on. There's also something to be said for the simple pleasure of mechanical engineering. An internal combustion engine is a beautiful piece of machinery. Pistons rising and falling, camshafts opening and closing valves, spark plugs firing in perfect sequence. There's an elegance to it that even the most sophisticated electric motor can't quite match. It's the elegance of a mechanical watch compared to a digital watch. One tells the time, the other tells time with style. So there you have it. Diesel engines and petrol engines explained in a way that hopefully made sense and maybe even entertained you along the way. We covered the origins, Otto's four-stroke cycle, and diesel's compression ignition breakthrough. We explored the key differences, spark ignition versus compression ignition, compression ratios and combustion characteristics, and that glorious diesel clatter. We examined their current roles, diesel ruling heavy transport and petrol dominating passenger vehicles. And we glanced into the future, An electric transition that's happening fast for cars, but much slower for everything else. If you found this video helpful, or if you learned something new, or if you're now the most interesting person at your next dinner party, consider subscribing. We make videos about the things you always wanted to understand, but never had explained quite right. Like a friend who won't stop talking, but a friend with production value and a fairly decent audio setup. And if there's a what is question you want answered, anything at all, put it in the comments. We read them. Most of them. Some of them. A statistically significant number of them. Thanks for watching. I'll see you in the next one. What if I told you there's a machine that can travel from New York to Washington, D.C. in under an hour? That's roughly the time it takes most of you to commute to work. What if I told you this machine runs on electricity? No fuel, no explosions, just silent, smooth speed that pins you to your seat, like a roller coaster designed by very polite engineers. And what if I told you this technology has been around for 60 years, yet most people have absolutely no idea how it works? Welcome to the world of high-speed rail. Today we're going inside the engineering marvel that connects cities at impossible speeds. We'll explore the wild history of how it all started, the rivalries, the disasters, and the sheer stubborn genius that brought us from steam to 300 miles per hour. We'll break down exactly how these trains work. No engineering degree required. I'll explain it so clearly, you'll be able to explain it to your confused uncle at Thanksgiving dinner. And we'll look at where this technology is heading, because the future of transportation might be faster than you think. This is What Is, and you're watching the answer. History and origins. To understand high-speed rail, we need to understand something fundamental about human nature. We've always been obsessed with going fast. The story starts, as many stories do, with competition. In the early 1960s, Japan was rebuilding. World War II had devastated the nation, and the economic miracle was just beginning. But there was a problem. The Shinkansen, the bullet train, was supposed to be impossible. You see, in the 1950s, train technology had basically plateaued. Trains in Europe and America topped out around 100 miles per hour. Engineers said that was it. That was the limit. Rails couldn't handle more, they claimed. Physics said no. Japan said, hold my sake. In 1957, a group of engineers at Japanese National Railways did something radical. They looked at the problem backwards. Instead of asking, how do we make trains go faster on existing tracks? They asked, what if we built entirely new tracks specifically designed for speed? It was an absurd idea. The cost would be astronomical. The engineering challenges were seemingly endless. But here's where the story gets good. They didn't just succeed. They revolutionized transportation. The 1st of October, 1964, just in time for the Tokyo Olympics, the Tokaido Shinkansen opened. The train was called the Zero Series, and it could travel at 130 miles per hour. That might not sound impressive today, but in 1964, it was absolutely unheard of. The old railway between Tokyo and Osaka took 6 hours and 40 minutes. The Shinkansen did it in 4 hours, for a journey that, by car, would take you 7. Now here's the part that blows people's minds. That original Shinkansen line has never had a single passenger fatality. Not one, in over 60 years of operation. Let me say that again. 60 years. 0 deaths from accidents. Compare that to driving, where approximately 38,000 people die annually in the United States alone. The Shinkansen is quite literally the safest form of transportation ever invented by humans. But Japan wasn't alone for long. France entered the race in 1981 with the TGV, the Train à Grande Vitesse, and they made it look easy. The TGV hit 236 miles per hour during testing, setting a world record that would stand for decades. The French didn't just copy Japan, they improved the concept in a way that nobody expected. The TGV used something called active tilt. You see, when trains go fast around curves, they experience centrifugal force. the same force that pushes you to the outside of a car on a sharp turn. Traditionally, this meant trains had to slow down for curves, or passengers would get thrown around. The French said, "What if the train leaned into the curve?" And they built it. The TGV could tilt up to 8 degrees, allowing it to maintain speed through curves that would force other trains to crawl. The competition heated up. Spain built the AVE. Germany built the ICE, the Intercity Express. Italy built the ETR. Every major industrial nation wanted a piece of the high-speed revolution. But here's the question everyone was asking. What about America? America tried. In 2000, Amtrak introduced the Acela Express, their attempt at high-speed rail. And it was fine. It was fine in the way that your friend's attempt at home cooking is fine. The Acela tops out at 150 miles per hour. In certain areas, when conditions are perfect, and everyone behaves, and the moon is in the correct phase. The problem is simple. America didn't build new tracks. They tried to retrofit old ones, and you can't make a thoroughbred racehorse out of a farm pony, no matter how much makeup you put on it. But don't lose hope. We'll get to the future. I promise. Alright, before we dive into the engineering, because that's what you came for, right? Let's take a quick pit stop. If you're finding this journey through the world of high-speed trains fascinating, hit that like button. It helps more people find this video. And honestly, it makes my day. And if you want to explore more What Is content, subscribe and hit that notification bell. We break down the most incredible technologies and ideas, and I think you'll like what you see. Now let's get into the good stuff. How it works. Okay, let's get technical. And I promise, I will make this make sense. The first thing you need to understand is something called steel on steel. That's exactly what it sounds like. A metal wheel on a metal rail. There's no rubber, no tires, no cushioning. It's just two pieces of hard metal pressed together. Now you might think that sounds inefficient. You'd be wrong, and here's why. When you drive a car, you're fighting something called rolling resistance. The tire squishes slightly as it rolls, absorbing energy like a sponge. That's why cars use so much fuel. A huge chunk of the engine's power goes into just squishing the tires over and over. With steel on steel, no squishing. The wheel is hard, the rail is hard, and they roll with almost no resistance. It's literally the most efficient way to move humans over land that we've ever invented. But here's the catch. Steel on steel has terrible traction. That's why your car wheels spin when it's raining. The rubber slips on wet asphalt. Trains solve this with weight. Trains are heavy, immensely heavy. A single locomotive can weigh over 200 tons. That weight presses the wheels into the rail with enormous force, creating enough friction to move the entire train. Now let's talk about how high-speed trains actually propel themselves forward. Electric trains like the Shinkansen and TGV get their power from overhead wires, those weird cables you see running above the tracks. The train has a device called a pantograph, essentially a metal arm that reaches up and touches the wire, completing an electrical circuit. This is where it gets beautiful. The train's motors are what are called three-phase AC induction motors. I know, that sounds like something you'd find in a Transformer movie. But stay with me. Here's the simple version. When you run electricity through a carefully designed coil of wire, it creates a rotating magnetic field. This field pushes on the train's wheels, causing them to spin. The key insight is this. Unlike a car engine, which has a limited number of power strokes per second, an electric motor can generate maximum torque, the rotational force, at any speed. That's why electric trains accelerate so quickly. In a petrol-powered car, you have to rev the engine to generate power. There's always a lag between stepping on the gas and feeling the acceleration. In a high-speed train, you step on the power and you feel it instantly. The motor goes from 0 to maximum torque in milliseconds. Now here's the part that really matters for speed. Aerodynamics. At 200 miles per hour, air resistance is the biggest enemy. Not friction, not the rails, the air itself. A train going 200 miles per hour is pushing thousands of pounds of air out of the way every single second. Engineers spend years perfecting the shape of high-speed trains to cut through the air like a knife through butter. Look at the nose of a Shinkansen. That long pointed front isn't just for looks, that's calculated aerodynamics. The train is literally designed to split the air in front and guide it smoothly around the sides, minimizing turbulence and drag. But aerodynamics creates another challenge: stability. At high speeds, airflow can actually lift the train slightly off the tracks, kind of like an airplane wing. That's dangerous. If the train lifts too much, it could derail. Engineers solved this with careful design of the front wheel arches and subtle spoilers that direct airflow downward, pressing the train firmly onto the tracks. Some trains even have small wings, yes really, that extend slightly to generate downforce at speed. Now here's the system that makes high-speed rail possible: signaling. At 200 miles per hour, a train can cover the length of a football field in just 2 seconds. There's no time for a human to see a problem and react. Everything must be automated. High-speed lines use something called automatic train protection, a TP. The system constantly monitors every train's position, speed, and the conditions of the track ahead. If anything is wrong, another train too close, a track problem, anything, the system can automatically slow or stop the train. This is why the Shinkansen has never had a collision. The computers are faster and more precise than any human could ever be. One more thing, because this is the question everyone asks: how do they stop? High-speed trains have multiple redundant braking systems. There are electric brakes, which use the motors in reverse, acting like generators to convert the train's motion back into electricity, sending it back into the power grid. These are called regenerative brakes, and they're incredibly efficient. There are also disc brakes, exactly like in a car, but much larger and more powerful. And on some trains, there's even an emergency magnetic brake that pulls the train against the rails using magnets. The result? A high-speed train can stop from 200 miles per hour in roughly 2 kilometers. That's about the length of 20 football fields. Fast? Yes, but safe above all. And that brings us to the final question, the one that matters most. The future. Where is high-speed rail going? The answer might surprise you. The next frontier isn't just faster trains, it's something called maglev, magnetic levitation. A maglev train doesn't touch the tracks at all, it floats. Here's how it works. The track contains electromagnetic coils, essentially powerful electromagnets. The train has its own magnets. When the train approaches, the track's magnets activate, creating an opposing magnetic field that lifts the train slightly off the surface. No contact, no friction, no noise. The Shanghai maglev currently operates at 268 miles per hour, the fastest commercial train in the world. Japan's L0 series maglev has tested at 375 miles per hour. 375 miles per hour. That's faster than some small aircraft. But even that's not the wildest idea. There's something called Hyperloop, a theoretical system that would move pods through near vacuum tubes at speeds approaching 700 miles per hour. The lack of air means almost no resistance. Theoretically, a pod could travel at speeds faster than sound. Now, is Hyperloop real? That's complicated. The engineering challenges are enormous. Maintaining a vacuum tube hundreds of miles long, dealing with expansion from heat, safety concerns, and of course the small matter of cost. But companies are working on it. Tests are happening. And in the world of engineering, never say never. Back here on Earth, the immediate future is already exciting. In France, the next generation of TGVs, called Avelia Horizon, will enter service in the mid-2020s. They use distributed power, motors throughout the entire train instead of just in the locomotive. This reduces weight, improves efficiency, and allows for more capacity. In Japan, the Cho Shinkansen maglev line is under construction, connecting Tokyo to Nagoya. When complete, the journey will take 40 minutes, down from the current 90. And in America? America is trying. The California high-speed rail project has been controversial, delayed, and expensive. But here's what's important to understand. They're building it. The first section between Bakersfield and Merced is under construction. It will eventually connect San Francisco to Los Angeles in under 3 hours. And other projects are following. Texas is studying high-speed rail between Dallas and Houston. Florida has Brightline, Nevada has plans. The point is, the interest is there, the demand is there. It just takes time and money to build. But here's what I want you to take away from this. High-speed rail isn't just a technology, it's a philosophy. It's the belief that we can connect people across distances, not as fast as planes, but fast enough to make car trips obsolete. It's the belief that transportation can be clean, efficient, and safe. In a world increasingly worried about climate change, high-speed rail is one of the most environmentally friendly ways to move millions of people. An airplane produces roughly 10 times the carbon emissions per passenger mile as a high-speed train. A car? Even worse. When you ride a Shinkansen, you're not just traveling. You're participating in one of humanity's greatest engineering achievements. You're moving at speeds that 60 years ago, scientists said were impossible. And you're doing it safely, comfortably, and efficiently. That's the future of transportation. And it's already here. So now you know. You know the history. How Japan said, "Hold my sake," and built the impossible. You know the engineering. Steel on steel, electric motors, aerodynamics, and automation working together in perfect harmony. And you know the future. Maglev, Hyperloop, and a world more connected than ever before. If this story of human ingenuity fascinates you, there's more where this came from. What Is exists to break down the most incredible technologies, ideas, and concepts, explained simply, told engagingly, and always with a bit of fun. If you learned something today, hit that like button. It helps this video reach more curious minds, and that makes this all worth it. And if you want to join the journey, subscribe to What Is, and hit that notification bell. Every day, we're exploring another question worth asking. Until then, I'll see you on the next one. Welcome to What Is, where we take the world's biggest questions and break them down into bite-sized chunks. Kind of like how ancient civilizations broke down massive limestone blocks, except with fewer heat strokes and slightly more sarcasm. Today's big question: what is a pyramid? And more importantly, why? Why did humans, separated by thousands of miles and massive oceans, all collectively look at a pile of rocks and think, you know what? That should be pointier at the top. If you ever looked at a Toblerone and thought this is the ideal shape for a tomb, then you're already on the same wavelength as the pharaohs. But there's a lot more to these structures than just being very large, very heavy triangles. From the deserts of Egypt to the jungles of Mexico, we're diving into the mystery, the math, and the occasional madness of the pyramid. Before we get started, do the algorithm a favor. Hit that subscribe button and ring the bell so you don't miss out on our future dives into the what and the why of our world. Alright, let's get triangular. First, let's define the beast. Mathematically, a pyramid is a polyhedron with a polygonal base and triangles at its sides that meet in a single point. Historically, however, a pyramid is a massive check-me-out from a ruler to the rest of the world. When we say pyramid, 99% of you immediately think of the Great Pyramid of Giza. And fair enough, it's the only one of the 7 wonders of the ancient world still standing. It was the tallest man-made structure on Earth for over 3,800 years until the Lincoln Cathedral was finished in England. And honestly, the cathedral only won because of a spire that eventually fell down. So in terms of longevity, Egypt takes the gold. Egypt didn't invent the pyramid in a vacuum, and they certainly weren't the only ones to keep the trend going. In Mesopotamia, modern-day Iraq, they built ziggurats. These were massive terraced platforms. They weren't sharp at the top, they were more like giant wedding cakes made of mud brick. At the very top sat a temple. To the Sumerians and the Babylonians, these were the literal homes of the gods. You didn't go inside a ziggurat to be buried. You went to the top to talk to the manager of the universe. Then jump across the Atlantic to Mesoamerica. The Maya, the Aztecs, and the people of the Teotihuacan were pyramid building pros, but their why is different. While the Egyptian pyramids were mostly giant do not disturb signs for dead kings, Mesoamerican pyramids were bustling civic centers. They had stairs, lots of them, because these structures were meant to be climbed. They were the stages for rituals, astronomical observations, and occasionally the kind of human sacrifice that makes modern HR departments look very reasonable. And we can't forget the Nubians in modern day Sudan. Fun fact for your next trivia night: Sudan actually has more pyramids than Egypt, over 200 of them. They're smaller, steeper, and built much later than the Giza trio, but they proved that the pyramid look was the ultimate fashion statement of the ancient world. Even in China, there are massive trapezoidal mounds housing the tombs of early emperors, like the first emperor, Qin Shi Huang. You know, the guy with the terracotta army? His tomb is built under a pyramid-shaped mound that we haven't fully excavated yet, because it's supposedly rigged with traps and rivers of liquid mercury, which honestly, respect. So why the pyramid? Why not a giant cube or a massive stone sphere? Well, for one thing, stones don't like being spheres. They like being flat, but the real answer is physics. If you want to build something incredibly tall using only gravity and manual labor, the pyramid is the sturdiest shape you can choose. The weight is distributed so that the base carries the brunt of the load, preventing the whole thing from collapsing under its own ego. It is the easy mode of architectural stability, even if building it is anything but easy. But the why goes deeper than just the it won't fall down. In Egypt, the pyramid represented the Benben. In their creation myth, the Benben was the first mound of dry land that rose from the primordial waters of chaos. By laying a pharaoh to rest inside a representation of creation, you were basically giving them a VIP pass to the afterlife. It was a stairway to heaven, quite literally. The smooth, sloped sides were designed to mimic the rays of the sun shining through the clouds. Imagine you're a peasant in 2500 BCE. You live in a hut made of reeds. You look towards the horizon and see a 480-foot tall mountain of white, polished limestone capped with a gold peak, reflecting the sun so brightly it looks like a fallen star. You aren't going to doubt that the guy living inside it is a god, and you're going to get back to farming your grain and keeping your mouth shut. It was the ultimate branding exercise. In the Americas, the why was often about the mountains. The Aztecs and the Mayans built pyramids to mimic the sacred mountains that surrounded them. These were the places where the earth met the sky. By building a mountain in the middle of a flat city, you were creating a sacred space where the divine could descend and the human could ascend. Now let's talk about the how. This is where the internet gets weird. Okay, weirder. If you spend 5 minutes on the wrong side of YouTube, someone in a tinfoil hat will try and convince you that aliens built the pyramids. Their logic usually boils down to ancient people were too dumb to move big rocks. To which historians respond, no, they were just really, really good at math and they had a lot of free time during the off season. Let's look at the Great Pyramid of Giza. It's made of roughly 2.3 million stone blocks. Some of them weigh 80 tons. They're aligned to true north with an accuracy of within 3/16 of a degree. How did they do it without power tools or a crane from Home Depot? Theory number one: ramps. Lots and lots of ramps. For decades, it was thought that there was one long straight ramp, but to reach the top, that ramp would have to be a mile long, which was more work than the pyramid itself. Current leading theories suggest that a combination of external ramps and an internal spiral ramp that allowed them to corkscrew the stones up to the summit. Theory number two: water and friction. We have wall paintings that show teams of men pulling a massive statue on a sled while someone at the front pours water on the sand. Archaeologists realize that if you can get sand just wet enough, you reduce the friction by half. It turns out that ancient Egyptians were masters of fluid dynamics. And who were these builders? Another myth: they weren't slaves. We found the builders' village at Giza. These people were paid laborers. They had medical care. We found skeletons with healed bone fractures that suggest they had access to pretty advanced surgery. They were fed prime cuts of beef and plenty of beer. In ancient Egypt, beer was basically a liquid paycheck. So the pyramids weren't built on the backs of the oppressed. They were built on the backs of well-fed tradesmen who were fulfilling their national service during the Nile's flood season, when they couldn't farm anyway. Now let's pivot to the Mesoamerican method. Take the Teotihuacan, located just outside modern-day Mexico. The Pyramid of the Sun and the Pyramid of the Moon weren't built all at once. They were like an architectural onion. Every few decades or century, a new ruler would come along and think, this is great, but it needs to be bigger. And they would simply build a new larger pyramid directly on top of the old one. When archaeologists tunneled into these structures, they find layers of history. It's a timeline of a civilization's growth, and unlike the Egyptian pyramids, which are mostly solid stone, many Mesoamerican pyramids were filled with rubble and earth, then faced with carved stone and vividly painted plaster. They were bright red, green, and yellow. They didn't look like the dusty ruins we see today. They looked like a psychedelic fever dream. But why did it stop? Why aren't we still building pyramids? Well, apart from the Luxor Hotel in Las Vegas, which we don't talk about, humans eventually realized that pyramids are incredibly inefficient. Think about the floor-to-space ratio. If you build a skyscraper, you have 100 floors of usable office space. If you build a pyramid, you have a massive mountain of rock with maybe 3 tiny rooms in the middle. It's the least efficient way to house people. In Egypt, the pharaohs eventually realized that a giant "Bury my gold here" sign in the shape of a triangle was an invitation for grave robbers. By the time of the New Kingdom, they stopped building pyramids and started hiding their tombs in the Valley of the Kings, cutting them into the cliff faces to be more discreet. It didn't work. Almost all of them were still robbed, but it was a valiant effort. In the Americas, the civilizations that built them eventually faced collapse, not just because they forgot how to build, but because of droughts, warfare, or colonial intervention. The jungle reclaimed the stone, turning the mountains of the gods into green hills until explorers discovered them again centuries later. So what is a pyramid? It's a testament to human obsession. It's what happens when a culture's religion, math, and political ego all collide in a single point in the sky. It's a reminder that we have always wanted to leave something behind that says, I was here, I was powerful, and I knew how to move heavy things. Whether it's the limestone of Egypt, the mud bricks of Iraq, or the volcanic rock of Mexico, the pyramid is our most enduring symbol of the eternal. It's a shape that refuses to die. If you enjoyed this deep dive into the world of ancient geometry, make sure to give this video a thumbs up. It really helps the channel grow. Also, we want to hear from you in the comments. Have you visited any of these pyramids? I've been to Egypt and I've seen the Great Pyramid and the Valley of the Kings, and it was awesome. If you had to build a massive monument to yourself today, what shape would it be? Are you a classic pyramid person, or are you feeling more like a giant stone dodecahedron? Let us know below. And if you're still feeling curious, check out one of our other videos. There'll be one linked on screen now. Thanks for watching What Is, and see you in the next one. Hey there, curious minds, and welcome back to What Is, the channel that dives deep into the questions you didn't even know you had, and sometimes the monsters you definitely hoped stayed in the myths. Today, we're plunging into the briny depths because we're tackling a creature that haunted the dreams of sailors for centuries, and an environment that still gives many of us the shivers. We're talking about the legendary Kraken, and exploring exactly why humanity seems to have such a profound existential fear of the ocean. The mythical Kraken, an introduction. So let's start with our star attraction, the Kraken. Just hearing the name probably conjures images of massive tentacles, crushing ships, and maybe even pirate ship or two. But what is the Kraken truly? Is it just a tall tale spun by bored sailors, or does it have roots in something real and truly terrifying? Origins of the myth, Norse sagas. Our journey begins, as many good monster stories do, in the chilly waters of Scandinavia. The Kraken, or Krake as it was sometimes known, first surfaces in Norse sagas and folklore from the 12th century onwards. Early descriptions painted a picture of a creature so vast it was often mistaken for an island. Imagine sailing along, charting your course, and then suddenly your conveniently located landmass suddenly decides to sprout eyeballs and a few hundred feet of suckered arm. That's a bad day at sea, folks. One of the most vivid early accounts comes from the 18th century Danish bishop Erik Pontoppidan, who, despite being a man of God, seems to have quite the flair for monsterology. He described the Kraken as an enormous animal, the largest and most wonderful of all the animals of creation, capable of devouring men and ships. It would rise from the depths, its massive body creating whirlpools that could drag entire vessels down. When it submerged, it left behind a rich, fertile sludge, which fishermen apparently loved because it attracted huge schools of fish. So the Kraken was not just a destroyer, it was also a sort of deep sea, eco friendly fertilizer. Talk about multi talented. Kraken's behavior and size. Pontoppidan's Kraken wasn't just big, it was cosmically big. Its body, he claimed, measured several English miles in circumference. Let that sink in. We're not talking about a big squid, we're talking about a living, breathing landmass. He detailed how its enormous arms, or horns, as they were sometimes called, could wrap around the tallest mast, pulling ships down into the abyss. Now you might be thinking, surely no one actually believes an island-sized squid was lurking out there. And while the more extreme claims were likely exaggerated for dramatic effect, it's the ultimate hold my mead story. The underlying fear of something impossibly immense and powerful beneath the waves was very real. The myth of the Kraken evolved, terrifying sailors and inspiring storytellers for centuries, morphing slightly with each retelling, but always retaining its core identity as the ocean's ultimate leviathan. It wasn't just a monster, it was the embodiment of the ocean's raw, untamed power. The real-world inspiration, giant squid. So if the Kraken wasn't real, what was? Well, as often happens with legendary creatures, there is actually a grain of truth, or rather a very large tentacled grain of truth. Enter the giant squid, Architeuthis dux, and its even larger cousin, the colossal squid, Misonychotusis hamiltoni. For centuries, these creatures were almost as mythical as the Kraken itself. Sailors reported seeing colossal tentacles, enormous eyes, and battles with sperm whales, but solid scientific evidence was scarce. It wasn't until the late 19th century that scientists finally got their hands, or rather their hooks, on a complete specimen of a giant squid. And what a specimen it was. While not several English miles long, the giant squid can reach lengths, including its two longest tentacles, of up to 43 feet for females, making it one of the largest invertebrates on Earth. The colossal squid, while slightly shorter, boasts a much heavier and bulkier body, with eyes the size of basketballs, the largest eyes of any animal known to science. Imagine those eyes staring back at you from the deep. These creatures live in the dark, deep parts of the ocean, and only occasionally washing ashore or being caught by deep-sea fishing trawlers. Their natural habitat means that human encounters are incredibly rare. But it's easy to see how a fleeting glimpse of one of these magnificent beasts, perhaps a tentacle or a massive eye in the murky depths, could be exaggerated into tales of the all-consuming Kraken. After all, if something that big is down there, what else could be? Distinguishing myth from reality. The Kraken wasn't just a giant squid. It was a giant squid on a diet of steroids, radioactive waste, and probably a few too many protein shakes. It was the giant squid elevated to divine ship-stinking status. The real giant and colossal squid are impressive, yes, but they aren't sinking ships or forming islands. They're mostly just trying to find some dinner and avoid becoming dinner themselves for sperm whales. Turns out the truth is stranger than fiction, and also it has way more suckers. But the Kraken is more than a magnificent monster story. It's a symptom of a much deeper, more persuasive human feeling, our profound and often irrational fear of the ocean itself. So let's peel back the layers of our own fears and ask, why do we, as a species, seem to be utterly terrified of the big blue wet thing? Primal fears, the unknown, and the lack of control. Firstly, there's the mind-boggling scale of it all. The ocean covers 70% of our planet's surface, and the vast majority of it remains unexplored. We know more about the surface of the Moon and Mars than we do about the deepest parts of our own oceans. More people have walked on the Moon than have ever visited the Challenger Deep, the deepest known point. It's a vast, dark, alien world right here on Earth, and the unknown is a primal fear for us land-dwelling creatures. What lurks beneath the surface? What creatures adapted to crushing pressure and eternal darkness might be down there watching? Then there's the loss of control. On land, we're adept. We stand firm. We breathe freely. We navigate with ease. In the ocean, we're utterly helpless without technology. Our bodies are not designed for it. We can't breathe. We can't see clearly. We're tossed about by currents and waves. Feeling overwhelmed and out of our element sparks an instinctive panic. It's the ultimate feeling of vulnerability. Specific threats, predators, and the deep. And of course, there are very real, very toothy threats. Sharks are probably the poster children of ocean fear. Thanks to movies like Jaws, an entire generation of beachgoers developed a healthy, if disproportionate, respect for what might be swimming alongside them. It's not just the teeth, it's the silent teeth. That sudden brush against your leg in murky water, and your brain immediately jumps to man-eating aquatic terror. Most sharks are harmless to humans, but our primal circuitry doesn't care about statistics when there's a shadow beneath the surface. Beyond the predators, there's the sheer terrifying concept of the deep. Imagine descending into the abyss. The light fades quickly, replaced by an inky blackness. The pressure builds, capable of crushing a submarine like a tin can. And in this oppressive darkness, life takes on a bizarre, often grotesque form. Anglerfish with their lures, gulper eels with their enormous mouths, creatures that look like they've been pulled from a fever dream. The deep ocean is literally alien. It's a place where the rules of our surface world don't apply, and it's profoundly unsettling. Other threats: drowning, maritime disasters, etc. The most immediate and common fear is, of course, drowning. Our very existence depends on air, and the ocean is the ultimate barrier to that. The feeling of being submerged, unable to breathe, is a fundamental, terrifying experience that all land animals instinctively avoid. Then there are broader threats: storms at sea, tsunamis, shipwrecks. The ocean's raw power has claimed countless lives throughout history. From ancient galleons to modern supertankers, no vessel is truly immune to the wrath of the waves. These real-world disasters feed our collective anxiety, reminding us that with all our technology, we are still small and fragile against the might of nature. The ocean demands respect, and sometimes it demands more. Psychological aspects, thalassophobia, and evolution. For some, this fear goes beyond a healthy respect and into the realm of genuine phobia. Thalassophobia. It's an intense, irrational fear of deep bodies of water or the vastness and emptiness of the sea. Sufferers can experience panic attacks, shortness of breath, and an overwhelming sense of dread just at the thought or the sight of a large expanse of water. From an evolutionary standpoint, it makes sense. Our ancestors were land dwellers. We evolved to thrive on terra firma, to see threats coming, to build shelters. The ocean was a boundary, a place of starvation and death for those who ventured too far out. This evolutionary imprint lingers, making us inherently wary of environments where our natural advantages are completely negated. We lose our sight, our hearing is distorted, our sturdy legs become useless flippers. It's an environment designed to make us feel profoundly out of place. It's basically a giant, wet, incredibly well-stocked monster closet. Connecting the Kraken to ocean fear. So how does the Kraken fit into all of this? The Kraken isn't just a myth. It's a personification of these myriad fears. It gives a face, or rather many tentacles, to the unknown vastness, the crushing power, the terrifying creatures, and the ultimate loss of control that the ocean represents. It's a symbolic monster that embodies everything we fear about the deep. By creating the Kraken, humanity gave form to its anxiety, making the amorphous terror of the ocean into something tangible, something that could be fought, or at least imagined fighting. It's comforting, in a strange way, to have a name for the thing that frightens you most. Ultimately, our fear of the ocean is a complex tapestry woven from primal instincts, real dangers, and the boundless stretch of our imagination. It's a fear that reminds us of our place in the natural world, small, vulnerable, and forever fascinated by what lies beneath the surface. Yet, ironically, this fear also fuels our curiosity, pushing us to explore, to understand, and perhaps someday to conquer, or at least coexist with the mysteries of the deep. What about you? What's your biggest ocean fear? Is it sharks, the crushing depths, or just the thought of something brushing against your leg in murky water? Let us know in the comments below. And if you enjoyed this dive into the deep, please hit that like button, share this video with fellow explorers, and be sure to subscribe to What Is for more journeys into the fascinating unknown. Stay curious, and see you next time.